Okay, good morning everyone. So in our last lecture we were doing motion in 2 and 3 dimensions, but we skipped over a topic on the previous chapter, which is in vectors, because it was a little bit too messy to do it all over Zoom. So let's go back to chapter 3 and just finish that off. So the thing that we'll need is unit vectors. So let's just recap that just for a minute. So unit vectors basically are something very similar to, or the notation that you use with unit vectors is something very similar to what you probably already know, which is coordinates. So for each of the x, y, and z coordinates, you assign a unit vector. That just means a vector which is length 1, which is pointing along the coordinate axes. So like here, I, j, k are the unit vectors along the x, y, and z axes. And we can rewrite any vector in terms of these unit vectors. So something with coordinates ax, ay, we can just simply write just like this. So ax times unit vector I plus ay times unit vector j. Okay, so all right, so we can add with these unit vectors, and the main thing that we wanted to get onto is this topic of multiplying vectors. And so you can multiply vectors in various ways. So the simplest way is just simply to multiply the vector by a scalar. So just multiply it by some number, and then the vector is always pointing along the same direction. If it's a negative number, then it'll be pointing in the opposite direction, but it's basically still sort of parallel to it. But we can also do vector multiplication, and we'll talk about 2 types of vector multiplication. So first one was the scalar product. This is well, schematically something like this. So you take 2 vectors as the input, and the scalar product, which is just represented by this blue box here, spits out a number, and the number that it spits out is given by this rule. So you just multiply each of the components together, and then you add them. Okay, and this is just a particular rule that somebody invented, you could say, but it turns out to be something which has some physical meaning, and it's got some nice mathematical properties, so that's why we consider this particular rule. But it is just a particular kind of rule, abstract rule, if you like. And so we worked out that it's possible to rewrite this scalar product in as this result. So this means the length of A and length of B multiplied by the cosine of the angle between them. And you can do this by using this fact that this is a quantity that is invariant with different coordinate rotations. And so this is a special property of this thing. It's not, going to always be true of any kind of formula that you write down. Like, if you write down some other formula, then you won't be invariant under rotations, but this one is. That's why it's sort of special and interesting. And right, and then we were getting on to vector products, and so this is what I want to just finish off today. And vector products had this pretty curious rule of if you want to multiply 2 vectors, then maybe I'll write it here again. So if you had 2 vectors, A was AX, AY, AZ, BX, BY, BZ, then this vector product has this particular rule where what you do is if you want to look at the x component, then you look at all the numbers that don't involve the x component, and then you sort of do this kind of cross multiplication move. So for the y's, it's cbx. Sure, that's right. Yeah. And this one was ax by minus ay bx, and that's basically the definition of the vector product. Okay. Now that's quite a sort of a handful to remember, right? Even I'm sort of like, I can't just sort of confidently write this formula down. You know, I'm always checking, did I get this sign right here? Are all these signs right? So there's a couple of methods to work out this vector product so that somehow you don't have to remember just this formula, right? The first one is using these unit vectors. So this is where, well, in my opinion, this is where the unit vector notation is actually quite useful. So what you do is you look at the, you first have to sort of remember, you still have to remember something, okay? So there's always something you have to remember, but it boils it down into basically it's sort of only essential components so that you don't have to remember so much. You know, this is what we like to do in physics and maths. We just sort of boil it down to some essential rule. And what we did last time was to work out the vector product of this one. And we did this example where we take unit vector I, unit vector j, and then we worked out using this formula that it was unit vector k. Okay. Now, maybe we can do another example here. So how about we do, okay, instead of I times j, maybe we can do k times j. Right? Okay, so let's do k times j. So what is k times j? So unit vector k times unit vector j. So firstly, let's write down what these things are. So k is jk, so it's like that, and j is the second one. So we're doing this particular case, and then we can just apply the formula. So so for the x component, what is this going to be according to the usual rule that we, or this rule that I've written down here? So firstly, what's AYBZ going to be for this case? 0, right. Okay, so it's 0 minus, and what's AZBY? 1, right. So it's 0 minus 1, which is minus 1. Okay, AZBX, what's this going to be? Right, 0, and then AXBZ, also 0. So that's just 0. And this one is AXBY, so what's that? 0, yeah. AYBX, also 0. So this one's 0. In other words, so this is minus 1, 0, 0. In other words, it's minus I. And that's what's written there. So minus of k minus j is plus I. So the kind of simple way to remember all these formulas here is to basically just remember this diagram here. And so the rule is that, you know, if it's I times j, then it's, you know, it's it's the one that is not there, right? So if it's I times j or j times I, so firstly it's going to be k because that's the one that's not there, right? So you've got I, j, then it'll give the other one. Now, the way that you remember the sign is if you're going around kind of in alphabetical order, well, in terms of like I, j, k, so if you're sort of going around in this kind of correct direction, then it's just the plus sign. If you're going around kind of the wrong way around, so if you're going j times I, for example, that's the reverse alphabetical order, then it will be a minus sign. So j times I will be minus k. J times k, so this is, we're going around the correct way in the circle, so it'll be j times k gives just I, or if you're going, it's the reverse order, k times j will be minus I. Now what if you, and likewise here too, so k times I is j, or I times k is minus j. What if you get two of these vectors? Now if you get two of these vectors, then it will be 0, and well, again, you can convince yourself of that by just explicitly working this out. So, maybe let's do k times k. So k times k. So in this case, both of these are 0, 0, 1, right? This is 0, 0, 1. This is 0, 0, 1. So ay bz. So in other words, it'll be this 0 times the z component, which is 0, and the azby will be same, but it's also 0, so that's 0. azbx will be, well, maybe it's easier if I... Okay, so azbx means going to multiply this one times this one, which is 0, minus this one times this one, which is 0. And for this one, we're going to multiply this one and this one, which is 0, and minus this one times this one, which is 0. So this is all 0. The 0 vector. So basically, any time that you are doing the scalar product, vector product with the same element, so I times I or j, it's always 0. And so we've worked out what the rules are for this for these special cases. Now how do I do the general case? So so maybe what I should do is to prove to you that I can recover this formula without remembering it, right? Okay, so this is what we do. So we first write A in terms of this unit vector notation. So like that. And likewise with B. Okay, and what we're going to do is, this is what we want to work out, right? A cross B. So when we do the cross product, vector product, okay, so I'm going to copy this out again. Bx I plus hy. Then I'm going to just multiply this whole thing out, right? So just treat these as some sort of algebraic variables, and just expand it out as if you're just doing your algebra. But you have to make sure that you don't change the ordering of these things. Okay, so there's actually 9 terms in general. There's 3 terms here, 3 terms here. There's 9 terms. But some of them will be 0, so we won't write them out. So basically we go through all 9 terms. So we multiply this one and this one. So this is I times I. So we already know that that's 0. So I'm not going to even bother writing that. Okay, next one is this one times this one, which will be AX BY. And I times J is, according to the rule, what is it going to be? K, right, yeah. So we write K. Here, I times K, what's that going to be?
Negative J.
Yeah, negative J. So negative AX BT J. Okay, so that's the first 3. Now I'm going to do this one, J times I.
Negative K.
Yeah, negative K. AYBX, negative K. This J times J is 0. J times K. I, right. Okay, so that's the next 3. And the final 3 is K times I. Right, J. I think somebody, it's either a cough or somebody said J. K times J. Negative I, yes. A, Z, B, Y, I. And K times K is 0. Alright, so we've got that. Then now we can just collect the terms because there's 2 Ks, 2 Js, and 2 Is, right? So let's collect the Is. So it's AY, BZ minus AZ, BY. Okay, good. Scared that it wouldn't work out, but it did. J's here, it's AZ, BX minus AX, BZ. K's AX, BY minus AY, BX. And just check that it gives the same thing. So AX, BY, AY, BX, yes. AZ, BX, AX, BZ, yes. AY, BZ, AZ, BY. So it gives the same result. And of course, this is general. So, for example, if these were numbers or anything like that, you could, of course, do the same thing. So this is one way that you can work out how to do the vector product. And basically, all you have to do is just remember this picture, right? So write it out with unit vector notation. Remember this picture, and then you should be able to work it. Make sense? Okay. That's method 1. Now method 2 kind of involves you knowing what the determinant is of a matrix. Who knows what the determinant of a matrix is, or who's familiar with that? Okay, so at least some of you, yes. So for those of you who are familiar with calculating the determinant, it's basically the same kind of rule that you are seeing here as calculating the determinant. If you don't know what the determinant is, then I guess this rule is not probably going to be so great for you because, yeah. So in the determinant way of calculating it, essentially you first arrange your, well, you kind of construct a matrix that looks like this. So the first row is just ijk always. So you just always put ijk there. Second row, you put the first vector. And in the third row, you put the second vector in the product. And of course, you've got to get these orders right, because in this vector product, if you get the ordering wrong, then you'll be out by a minus sign. And then from there, basically, you just calculate the determinant of this particular matrix. And when you normally calculate the determinant of a matrix, it's just numbers, right? So you get a number at the end. In this case, you have, because you have vectors in this first row, you will actually get a vector at the end, right? Is this a typo? This looks like a typo. Okay, yeah, this must be a typo. This has to be I, J, and K, right? Yeah, so I don't know, I just copied this from somewhere, but this is a typo. Okay, so when you calculate the determinant of a 3 by 3 matrix, what you do is for a 2 by 2 matrix, it's like the product of this and this minus this and this. So if it was just that, it would be that would be the determinant. But in a 3 by 3, basically what you do is you calculate the determinant by multiplying the product of this determinant multiplied by this element, and then then you look at this row. This element. You delete the rows and columns corresponding to that. Then, the second one has a minus sign according to the definition of determinant. The way that I like to think of it is that it's kind of like it's wrapped around in periodic boundary conditions, if you like. So I would probably write this with a plus, but then AZ, BZ to AX, BX. Whatever way you prefer. And then the third one, this thing should be K, and then the determinant of this 2 by 2. And that's basically, that is method 2. So it relies on you knowing how to calculate determinants. Okay. In general, if you want to work out what the vector product is, you have to get down and calculate it according to what I just, according to one of the methods that I just described. But you can roughly work out what direction the vector should be by using this so-called right-hand rule. So this thing appears in lots of different physics contexts. So, when you learn electromagnetism, you're often doing things like this. But it's, I guess, a more general rule in a way, because this is basically the rule for working out which direction a vector will point after you do a vector product. So there's different variations of this, and some people use this one where you remember which finger is which vector, or this one, which I think is the one in the book. According to this, the fingers here this is the first vector, and then the palm is the direction of the second vector. So imagine a thing pointing out of your hand. And then the thumb tells you which direction the vector product is. So here, you first point your hand this way. So if we're trying to work out at least the direction of the vector product for these two vectors here. So we've got first vector here. And okay, so this is not at right angles, but you can see that at least it has some component in this direction. So basically you just take this vector as being sort of, right angles to vector A. Basically, the angle will just change the magnitude of the vector, so it doesn't really change the direction. So it's not going to really change the result according to this right-hand rule. So the palm is pointing along this way, so that because the B vector is that way, or more or less that way. And then the thumb is telling you which way the result of A cross B is going to be pointing. So it's going to be this one. Now, okay, so if it was, I think this is trying to do B cross A. Yes, B cross A. So if it was the other way around, so if we're doing B cross A, then you've got to do some contortions to get fingers along B, and then because A is pointing now this way, twisting your hand around like this, and now this time the resultant vector will be going down. You can remember whatever rule you like. You know, some people prefer the finger ones like this. You have different definitions, but so long that you stick to the correct definition and you stick to the right hand. This is what they'll call the right hand rule, because this is probably the easiest mistake that you can make, that you're writing something down and you're trying to work it out, and then you use your other hand that you're not writing with, right? And then you get exactly the opposite answer. So you've got to always use the right hand rule. Okay, and so as I was saying, this is more or less, what I consider to be the definition of the vector product. So you do this bizarre kind of whole, multiplying with, and then subtracting, this kind of deal. But often, because this looks a little bit complicated, it will be introduced to you perhaps in this form. But in fact, this is, I think, not really the definition of it. This is actually just the a kind of another way of calculating what this vector product is. And so you may have seen that if you want to work out the magnitude of a vector product, then it's AB sine theta. So the scalar product was AB cos theta, but this time it's sine theta. And so the way that you can work this out, following from this particular rule, is, again, you use this fact that this quantity is invariant under coordinate choices. So despite this very bizarre looking rule, if you rotate your coordinates and you calculate the vector product, you'll actually always get the same answer, which is pretty surprising in a way. It's such a weird looking rule, and so what must happen is that when you rotate your coordinates, essentially the effect, of course, it'll change all these vectors, right? So when you rotate your coordinates, now your A vector will be a different vector. Well, at least on paper, it looks like a different number. And B will be a different vector. But somehow, both of those changes kind of cancel each other out somehow, and you still always get the same number. So it's kind of a bit of magic. It's sort of mathematical magic there, right? And so you use that property to work out this thing, and we choose a coordinate frame so that it's relatively easy to calculate this thing according to this formula. And so again, so what we do is so we've got these two vectors, A and B, and we rotate the coordinates so that one of the vectors points along, say, the x component of the axis. And then if you do that, right. Okay, let's squeeze it here. The rest. Well, put that there. So we're going to choose our coordinates so that A is pointing exactly along the x-axis. So we can choose our A to be basically this one. And we can always do that because we can just rotate our coordinates to do that. And then what we're going to do is we're going to oh, I see, yes. Okay, and sorry, forgot to mention that we can also always choose the coordinates so that the Z component of these coordinates that we're choosing, this is kind of right angles to these two vectors. So imagine if you take any two vectors in space, right? So just point them like this. You can always draw a plane through those two vectors, and so there's always some direction which is going to be orthogonal to both of those two vectors, because you know, you just have a plane in three-dimensional space. There's always a vector that's orthogonal to that plane, right? So we can actually always choose B to be in such a way so that it is the Z component is always 0. So we're going to choose Z component. So you know, we're choosing a very, very convenient and special frame in relation to these two vectors. But B is not necessarily going to be parallel to A, so we have to put in some angles here. And so if there's some angle theta between these two vectors, so B, A, theta, phi, then the x, because we define the x-axis this way, right? And we're going to define the y-axis this way. The z-axis will be right into the board. So this will be b cosine theta, and this will be b sine theta, phi, sorry. So we can always choose our coordinates in this particular way for any arbitrary vectors. And then we just substitute it into the vector product formula. So we can sort of use any of the methods that we did before. So well, let's just sort of follow the formula here in this case. So in this case, for the x component, we look at the y and z ones, and then we do 0 times 0 minus 0 times 0. So this is 0, right? Yeah, that's right. For the y component, we look at the x and the z. So we do, I think, 0 times this one minus 8 times 0, which is 0. And then for the z component, we look at the x and y components. And then so we do this one times this one minus this one times this one. So this is AB sine theta, phi, sorry, minus 0. And so that is the result of doing this. And then so we can see that the magnitude of this vector will be AB sine phi, as we got there. And the direction will be in the z direction. And it's going to be orthogonal to both of these vectors. So this is consistent with the right-hand rule. So remember the right-hand rule, we use our fingers for A, and then the palm for B this way. And then so the thumb is telling you which way it's pointing, so it's going to be pointing out of the board, which is the Z direction. Okay. Okay, all right. So let's try this question. So vectors C and D have magnitudes of 3 and 4 units. What is the angle between the directions of C and D if the magnitude of the vector product is 0? Right, yeah, zero degrees, yes. So basically we just apply this formula. So C and D, well, okay, so A and B, but the magnitudes are 3 and 4 units. So this AB will be 12, right? Now, only way that this can be, well, actually it's not the only way, but a way that it will be 0 is if this angle between them is 0, right? Sine 0 is 0. So is there another way that it could be 0? Right, yes. Okay, so I've got a bit of a mixture, but sine of phi is 0 if it's 180 as well, right? Because sine is this, right? So sine is, so here's 180, that's 90, 270. So it could actually equally be 180 degrees. So basically, you know, the deal with the vector products is that if the vectors are parallel with each other, so in the first case it was like 3 and 4, the lengths of them. If it's like this, the vector product will be 0. But also if it's like this way, okay. So either way will be 0. So what if the resultant was 12 units long?
90.
Right, 90. What about the other answer, 270? Does that work? Yes? No? Who thinks yes? As in, 270 is also a valid answer. Okay, who thinks no? Okay, we're getting no answers here. Okay, so I think it is a valid answer too, because if it says the magnitude of the vector product, right? So all this would change is the direction of the resultant vector. Yeah. So you know, if it's 90 degrees, here's 3, here's the one that's 3, and the other one that's 4. It's like this, right? So that essentially, you know, according to right-hand rules, this resultant would be into the board, right? But if it's, this is 90, but if it was 270, this 4 would be pointing this way. It's actually also 90 this way. So this time it would be out of the board, but that's just the direction of the vector, and it says the magnitude of the vector, and so I think either are valid. Yeah. Okay.
Question.
Oh yeah.
Remember that the kind of the angle between two vectors should be between 0 to pi.
Well, 270 is between 0 and 2 pi, yes.
0 and pi.
Oh, 0 and pi, okay. Okay.
Or is that just a math definition then?
Yeah. So I'm not going to say that that's wrong, because probably, you know, it's designed so that you will not get the, you know, wrong answer given some formula, right? So for example, you know, here we've got AB sine theta, right? And then it sort of depends upon like how you define the angle, I guess, between them. So if you you know, you would say that, well, here is also the angle between them, right? So this was the 270 case, right? Right. So that's the angle, sort of. If you say, you know, well, it's defined with respect to the angle between them, in that case, then you would kind of get the wrong answer because, you know, if phi is the angle between them, then this will be positive, whereas for 270 it should actually be negative, right? I think it depends on how you define phi, and over here we define phi in this way. So here's the angle phi, and so we define phi as the angle so that it's pointing in this y direction. So these would be both positive values if you choose the angle defined this way, but then if you define this angle to be negative, then of course this is going to be a negative value. So so long that you're kind of consistent in your definitions, then I think it's not really a problem to have angles that are larger than 270. So for example, here 270 that would be defined like some angle like pointing this way, right? And then I get the correct sign here, right? Yeah. But then if you defined it as the angle between them, then I would start to get the wrong answer, right? So yeah. But in any case, for this one, this is just really talking about the magnitude. So it wouldn't actually matter which way you define it. Okay. So can the sum of the magnitudes of two vectors ever be equal to the magnitude of the sum of the same two vectors? All right. Give you a minute to think about that. You can discuss it if you like. Okay, so who thinks yes? Who thinks no? Who doesn't understand the question and needs explanation? All right, well, let's see the puzzle. So let me just visualize it a bit. So we've got two vectors. All right, so let's call them A and B. So the magnitude of the vector is, of course, just this length. So maybe we should make sort of some kind of different lengths. So that length of A and length of B, right? So this is, I think well, okay, let's just stick to A. So A is this length, and this is B, right? Length of these two vectors, yes. So the sum of the magnitudes, right? So the sum of the magnitudes, that means A plus B. And the magnitude of the sum of the two vectors, so the sum of the two vectors, in other words, A vector plus B vector, so this is going to be some vector which is going to be like, looks like this, right? So here's the resultant vectors, C. So basically, it's saying, can this be equal to the length of C? So, could it be equal to the length of C? So in this case, just for this particular example that I drew on the board, is C equal to the length of A plus B? No? Okay. Is it bigger or smaller? C. Smaller, yeah. Smaller because, I don't know, this is a longer way around, right? C is the direct route, A and B is the diversion route, right? But it's saying, can it ever be? So, these are just two examples that I chose. Maybe a different example, it is equal. Or do you think that's impossible? Right, yeah. If it's parallel, then... Yeah, yes, exactly. So if it's the same direction, then you'll have this situation where A and B will be like this, and it will be equal, yes? Right? So that's when the sum of the magnitudes will be equal to just the sum, the magnitude of the sum. Yeah. Okay. All right. So this question, it's probably it sort of appears harder than it looks, right? Like, so when you look at it, you just go, okay, well, this seems very hard. But if you actually start to break it down and draw some diagrams, then so in terms of the result, it's kind of much easier. Okay, so let's go back. Any questions on vector chapter? Anything you want to talk about in there? No? Okay. Oh yeah.
I still have a question about the polar coordinates of the vectors. So the phi between the phi of sine cosine is
like here, yes.
Angle between the vector and the coordinate points and the axis.
Oh, I see.
Or is it between?
Like in the vector product, like over here, this one, this phi here, or
no, this. For example, this one.
Yeah. So this one is the angle between the vectors, right? And so it's this angle here, between A and B, right? So it's not the angle between A and then the axes or anything like that. It's the actual angle between them. And also, this is a three-dimensional problem, so I've drawn it kind of conveniently on a plane here. But if you have a general situation where these are pointing in some funny direction like this, it's what you do is you look at these two vectors, and then you have to imagine the plane between them, and then in that it's the angle in that plane. So that is basically what that phi there is. Yeah. So it's the angle between the vectors, and it's kind of like in the plane of the two vectors. Same with the scalar product. So when you when we talked about this, oh sorry, this one. This is the angle, same angle between them. But when we derived this thing, this angle here was actually also the angle in the coordinates, but that was only because we chose special coordinates, because we aligned the coordinate, so it's along A, right? So that was a special case. In general, this angle would not be like the angle with respect to the coordinates. Yeah.
And what is the problem about the negative sign?
The negative sign, yeah. So the problem with the negative sign is just how you actually define it. So there's not really a problem here, because this is purely talking about the magnitude of the angle. So even if you defined it, even if you sort of somehow took the wrong angle, right? So say instead of taking the angle between them, and then you took the other angle, you would just get the wrong sign. And this formula is just looking at the magnitude anyway. So in terms of this formula, you would just define it. The probably easiest way is just look at the smaller angle, right? And then that would give you the magnitude. And then for the direction, you use the right-hand rule, right? So that's kind of the line of thinking for this formula, where you are trying to work out just the magnitude, and then you separately work out what the direction here is. But over here, I took a slightly different definition of not necessarily the angle between them, but I set up my coordinate axis, define the angle here, phi, right? So in this situation, actually, this would still work even if I took, if I had the vector that was pointing kind of, say this way around, right? Because I've defined the angle as being kind of like the angle as not necessarily between the two vectors, but kind of in this positive angle direction. So I've started in the x direction, and then so this direction would be something to like 300 degrees or something like that. Okay, so if I define it more like that, then if I put in the 300 degrees here, then basically what will happen is that this will then be the negative value of if I took the angle between it, right? And in terms of the cross product, that would be completely correct. So so basically, okay, so I feel like I'm kind of confusing you here, but basically there's kind of two ways of doing it. So the way that it's done in the book is to say, okay, here's the angle. You always take the angle between the two vectors, and then for the direction, use the right-hand rule. So that's kind of the way that it's presented in the book. Here, I've done a slightly alternative approach, if you like, where I've just defined the angle with respect to the axis, and this angle is always in this positive clockwise orientation. This is actually the usual way that you define polar angles, right? And then in this case, if I define it like that, I don't really have to change anything, even if it's gone over 180 or anything like that. I just put in that angle there, and I will still get the correct answer.
So for instance, if we have 270 degrees between these two angles, the book will use negative 90 degrees, but you will use 270.
No, I think if it was pointing this way,
yeah.
I think the book definition would say, okay, always take the angle between them, right? And then so you would say that the angle is 90, right? Yeah, and then that gives you the magnitude, and then separately work out the direction with the right-hand rule, right? I guess in my method that I'm saying here, just always take the angle with according to this one, right? take the angle in this clockwise direction with phi, which is the usual polar angle kind of definition. So in this case, use 270, and then basically this formula will work for any value of phi. Okay, so sorry, that might have been a bit confusing because I departed slightly from the logic of the book, right? But this way of defining polar angles is actually probably pretty conventional too. So okay. All right, so let's get back onto motion in 2 and 3D. So just to quickly recap, so we did position vectors, displacement vectors. That's just a change in the position vectors. So basically final position minus initial position. Average velocity, so all these formulas look a lot like the case for 1D, where you look at the displacement, divide by the time, but now the position and velocity vectors are all vector quantities. Time is, of course, a scalar, so just dividing by some number. Okay, what did I miss here? Oh yeah, instantaneous velocity is, of course, the velocity that it's moving at exactly that moment in time. And definition-wise, it's sort of kind of the limit as you look at two extremely close together time intervals. So, or simply just a derivative of this vector. So computationally, you just it's actually kind of relatively easy. This looks like a complicated calculation, but if you just know the usual rules of calculus, then if you got your formula for the position coordinates, then you just throw it into the derivative, and then just calculate time derivatives, and then you can just calculate the velocity vector in that way. So acceleration is similar kind of thing. So instead of looking at the position, now we're looking at the changes in the velocity. So average acceleration is the change in the velocity divided by the time. Instantaneous acceleration, again, you take the time derivative and then you get the acceleration. And so we looked at sort of an example of motion in 2 dimensions mainly, which is projectile motion. So this is a special case when the acceleration is of kind of this form. So we're looking at a case where the acceleration in the x direction is always 0, and acceleration in the y direction is negative g, so it's just acceleration due to gravity. And why this is not working? Here we go. And basically the key point here is that the x and the y motion, you can more or less consider them separately. So even though it's a single particle and it's moving in some fashion, the x equations of motion don't really depend anything on the y equations of motion, except for the fact that it's the same object. So this is just to prove to you that kind of just projectile motion is just these two things happening at the same time. It's a sort of combination of something just going up and down and something moving across at constant velocity. This is some experiment to show that. This was this case of shooting a can from a gun, and you can show that essentially this is how you can always guarantee that it always has the same position. Yeah, and so, classic kind of physics problems that you'll encounter are things to, work out like the coordinates of projectile motion, and essentially what you do is to apply these 5 equations that we already learnt and apply it to this particular case. So we learnt these 5 equations in chapter 1, and so these would apply to the vertical direction of the object. And the horizontal component is much easier because it simply just travels at constant velocity throughout its movement, right? So, you can view this as setting a to 0 in these equations. So, for example, if you just set a to 0, then this just says the initial velocity is the same as the final velocity. Or here, just things like the position is speed times time. But the equations are kind of so simple that you almost don't need the formulas. Just speed times time is position, and so forth. And of course, yeah, that's right. So usually it's launched at some angle and there's some initial velocity, so you can work out the x and y components using some trigonometry like this. So the x component is v naught cos theta and the y component is v naught sine theta. Yeah, so this is where we got up to, so maybe we can just do a couple of these and then finish up. So if we wanted to oh no, so this is not where we got them. Oh, sorry, so yeah, we actually did cover this. Right, so this is just looking at the particular case of substituting the gravity into these equations, and so if you look at this case where it's launched at some angle and it's gravity, then you get these equations. Just visualize some of these equations. Right, so sorry, this is where we got up to. Okay, so from some of these equations we can work out the equation of the path. So this basically means we've got this object which, if you looked at a video of this, then you would see that it's moving in a parabolic shape, right? So you can sort of see that this shape here is a parabola here. So there's some parabola, so we can derive the actual equation of the shape of the motion by combining 2 of these equations. So as we said, the horizontal motion is, so the x coordinate is, so the initial velocity times cosine of theta, because that's the x component of velocity, times time. So this is basically just speed times time, right? It's the position. And the y component, we can use our second equation. So remember, is our, just apply this equation, the second equation, which we can get, we apply it to the y movement case. So the initial velocity is v naught sine theta, say upward direction, and we've got this half g t squared where we've just put in the acceleration is equal to minus g. Okay, so we can just eliminate t from these 2 equations. So what we want is an equation that actually gives you the path of the actual trajectory. So it's just a simple substitution kind of exercise. So from the first equation, from the x motion, we can say that t is equal to x divided by v naught cosine theta. and just substitute it into the y motion equation, which is v naught t minus half gt squared. So, okay, put that in there. So we're going to get v naught sine theta x divided by v naught cosine theta for the first term, and half g, and then we've got to square this thing, so it's x squared v0 squared cosine squared. Sorry, missed that. And just simplify this a bit, so v naughts cancel. We've got tan theta x minus, simplify this anymore? Not really. So g x squared over 2 v naught squared cosine squared. So, this is not the kind of formula that you would bother remembering because it's messy, it's got a bunch of difficult to remember kind of factors. So, so I would, if necessary, you would just derive this on the spot. It just takes a couple of lines. But you can see that basically this is a quadratic equation. So it's y is the height of the object. X, this is a horizontal position, and so we've got an x squared and an x. So this is kind of quadratic. All these other factors are basically constants. So here's our launch angle, theta. Here's just gravity. Here's the initial velocity. And so basically has the form of ax squared and bx plus c. In this case, the constant term is actually 0. So we could equally factorize this, and we'd have something like this. So tan theta minus x gx over 2v0 squared. And so if we solve this, say, for 0, then what this x here is telling you is that, at position 0, the height is 0. So basically, if we were to plot this, there'd be one point here because at position 0, the height is 0, but there'll be another point where the height is 0, somewhere over here, and that would be when all this stuff here is 0. So you could rearrange this bottom equation, this thing in the brackets here, set it to 0, and that would tell you the other position where if we're on level ground, then that would be the other position where it hits the ground. In fact, I think that's what we do the next. Yeah. So we can actually do this 2 ways. So we could do it from this equation, I think. Or we could do it the way that it's given here. So the range is basically, assuming we're on flat ground, how far does the projectile actually go? So the way that I've done it here is to use, again, like the second equation of motion, so the one with the t squared in it. So we can work out when the y position is 0 again. So this one is a function of time, right? So the y position is 0, and if you look at this equation, then we can factorize it for t. So if we just start with this equation here and then factorize t, so we can factorize t out there. We've got v0 sine phi minus half gt. And so if we plot this with time, actually, we'd also get some kind of parabola, actually, I think like this. So y like this. But this time, this is telling you when it actually hits the ground, right? So this is saying that, okay, so at this particular time, the height is going to be 0 again, i.e. it's going to hit the ground. So we can work out what that time is by just setting this part to 0. This part is just saying that at t equals 0, your initial height is 0. So just rearrange it. Half gt. So in other words, 2v0 sine phi over g. That's time. And we can work out what the position is because we can just use our, position is speed times time formula. So initial velocity is v0 cosine theta. Just substitute this stuff into here. So you get 2v0 squared sine theta cosine theta divided by g. Which you can slightly simplify using the trigonometric identity. 2 sine theta cosine theta is sine 2 theta divided by g. Yeah.
The x equals v0 cos theta t is the point on the projectile path at a specific time.
Yeah, it's the x position at a particular time. Yeah.
On the path of the projectile.
Well, if you view basically, this thing's flying through the air, and so that's a graph with time, right? But here is, at any given time, it will have position x, y, right? That's the vector for it. And both of these things are actually time-dependent things, right? So the x and y coordinates are changing with time. So this thing is just a formula to tell you what is the position at a particular time. And finish up here, but so I think we can equally work out what the range is from this formula too. So we could equally set this stuff here to 0. So let's see if that works. So then we'd have gx over 2b naught squared cosine squared theta is equal to tan theta, which is equal to sine theta over cosine theta. And just rearrange this equation for x. So it'll be 2v0 squared cosine squared sine theta over g cosine. This cosine cancels. And then we've got the 2v0 cosine theta g, which is the same thing as this. So we could have equally got it from this equation, so whichever one you like. Okay, so that's the range. Okay, so I think we'll finish up there for today. I think the homework you're supposed to hand in today, this week, because Tuesday was Zoom lecture. Okay, and then we'll see you next week.